I've been thinking about constructor theory a lot in the past few years. So constructor theory is this theory that David Deutsch proposed, and it's a proposal for a new fundamental theory to formulate science in a completely different way from the prevailing conception of fundamental physics. And it has the potential to change the way we formulate science, because it's a new mode of explanation. And what I mean by that is that so when you think about physics, you usually describe things in terms of initial conditions and laws of motion. And so what you say is, for example, where a comet goes, given that it started in a certain place and time. But actually, in constructor theory, what you say is what transformations are possible, what are impossible, and why. And the idea is that you can formulate the whole of fundamental physics this way. And so not only you say where the comet goes, but you say where it can go. And this incorporates a lot more than what's actually possible to incorporate now in fundamental physics. And so David and I have been working on this together for the past 3 years, and we've been applying it to many different problems. And so far, the two completed parts of this, trying out constructor theory to see whether it can solve problems, are a fundamental theory of information within physics, and the constructor theory of life, which is applying this new theory of information to a fundamental problem that's in boundary between physics and biology, and has to do with how are certain features of living things, such as the ability to self-reproduce very accurately, compatible with the laws of physics as we know them. And so I think in these two cases, in both cases, you can see how switching to this new mode of explanation allows you to change the perspective and address the problems in a much more effective way. And these are two examples where actually it makes all the difference switching to this new mode of explanation. So take information, for example. Information is something that we use in our everyday speaking, and also we use it in physics a lot. But for instance, we assume that information has certain properties, that it can be copied from one physical system to another, and other properties. But so far, we didn't have a fundamental theory telling us what are the regularities in nature which allow the existence of information in this sense. But actually, whenever we talk about information, we refer to those regularities. We assume that the laws of physics allow copy processes, for instance. And so in constructor theory, you can express these regularities, and this is what our theory does. So our way of incorporating information in fundamental physics is by formulating what are these regularities in nature that allow the existence of information. And so to see how switching to the formulating science in terms of possible and impossible tasks is crucial to solving this problem, you can consider what happens when you try to say that something contains information. The fact that something contains information has to do with the idea that you can swap that thing with something different. So it's what philosophers call a counterfactual property of the object. It has to do with what tasks you can perform on the object. That is to say, you can swap it with something else. So if you think of a flag, you can, it brings information only if you can swap it with a flag of a different color to signal. And this idea was not expressible in terms of initial conditions and laws of motion, but it can be expressed in terms of possible and impossible tasks, and as an intrinsic property of the flag of the object. So this is an example of how switching to this mode of explanation can address a fundamental problem in physics. Then there's a question, so this is classical information, but we know that there's something more, what we have been calling quantum information. And it's very interesting that in this constructor theory of information, you can relate in an exact way the notion of quantum information to that of classical information. And so you can, you have a unifying framework where you can describe both. And this is very promising because we've been searching for example, we've been searching for this theory of the, we've been searching for realizing the universal quantum computer for a long time now. And one of the reasons why I think we haven't yet succeeded in finding a way to implement that is that we do not have a good understanding of how quantum information is related to classical information. We don't have an exact expression for that. Actually, we didn't have. And now, if we have a theory where we can talk about in a unified way about quantum information and classical information, then there's a way of relating the two exactly. And so there is a way of understanding better what are the properties of the universal quantum computer that we want to realize in the lab. So that's also, this could inform the search for the universal quantum computer. That's also a very interesting thing. Then the idea of information is also very central to life. And this is the other example of how constructor theory can address certain problems that have been considered problems for long. So if you look at something like a bacterium, physicists have been particularly impressed by the fact that it's capable of performing tasks to a very high accuracy, retaining the property of doing so again. And also, so this is very much like a car factory, for instance, but the bacterium has also another property, that is to say it can create a copy of itself. And that's very, it can construct a new instance of itself. And that's a property that is very specific to life as we know it. And so one might ask whether such entities like bacteria and so forth that are fundamental to biology are compatible with the laws of physics as we know them, or whether they require something more than the laws of physics as we know them. Because the laws of physics are, quantum physics and general relativity and so forth, they are very, they refer only to elementary things like quarks, atoms, and so forth. They don't contain self-reproducers, let alone accurate ones. And so in fact, Wigner had this problem, and he proposed an argument according to which we should complement the laws of physics with some new designed ones to accommodate for properties like accurate self-reproduction. And if you apply the tools of constructor theory to this question, is an accurate self-reproducer like bacterium possible under the laws of physics as we know them, laws of physics that don't contain the design of biological adaptations? Well, not only you see that Wigner's reasoning was misled by using the prevailing conception of fundamental physics to address this problem, but you also see that constructor theory, in which the idea of something being possible or impossible is a natural statement, can address the problem very effectively. And you can also use the theory of information that I was describing before to tackle the question. And it turns out that, yes, what a bacterium does is compatible with laws that don't contain its design. And the only requirement on the laws of physics for that to be possible is that they allow for information in the sense that I was saying before. They allow for those interactions, like copying-like interactions, to be possible. But copying-like interactions that are not designed for a bacterium to undergo self-reproduction. So very non-specific interactions, elementary ones. And the key to the way a bacterium performs its own self-reproduction is the same as to, is the same as the key to the way a car factory constructs a car. In both cases, there's a recipe, a bit of information that has the ability of directing a construction process, of causing a task to be performed, because it contains the knowledge about how to perform it. In the case of the bacterium, it's the DNA sequence in which the bacterium is described. And in the case of the car factory, it's the sequence of elementary steps to assemble a car out of elementary components. And now, this particular kind of information is this sort of recipe, can also have an exact characterization in constructor theory, because it's information that can act as a constructor, as an object that can cause transformations and retain the property of causing them again. And so all these elements that I've just mentioned, information, knowledge, are emergent things that in the prevailing conception of fundamental physics would not have a natural expression, because you would have to talk about many atoms doing certain complicated, undergoing certain complicated transformation in some phase space. While in constructor theory, they are natural objects. They are the simple objects of the theory. I mean, they are the very elements by which the theory expresses itself. And so these are examples of how constructor theoretic devices that are new to physics can address problems that have been unsolved so far. And so that's very promising, I think. What are the fundamental ideas of the prevailing conception of fundamental physics that would be impacted by constructor theory? Well, the first thing to say is constructor theory accommodates certain things that the prevailing conception has been handling very well, and so it's a proposal to go beyond that, but not to contradict it. Yet it also has a radically different perspective on things, because as I said, in the prevailing conception, the fundamental objects are the laws of motion and the initial conditions of our universe. In constructor theory, on the other hand, the fundamental ideas are transformations that are possible and impossible, and explanation of why they are possible and impossible. So, and it turns out that under our laws of physics, in order for any transformation to be achieved, knowledge must be brought about in order to make that transformation performable to higher and higher accuracy. And so knowledge, which is a causal sort of information, and information with a causal power that has the ability of remaining instantiated in physical systems, is a highly emergent object, because it can't be just handled in the prevailing conception of fundamental physics. While in constructor theory, it becomes one of the central objects. So it becomes fundamental because it's the way accurate transformations can be performed in a world where the laws of physics are simple and do not contain any design. they don't contain those transformations. So here's an example of a change in perspective. And this is also an interesting take on, the idea that, humans are knowledge-creating systems. So one of the ways knowledge can come into the world is by natural selection, out of no knowledge, and another way is by humans creating it. So it turns out that in the constructor theoretic view, humans or knowledge-creating systems are quite central to fundamental physics, but in an objective way and not anthropocentric way. So this is a very deep change in perspective. And I think one of the ideas that will be dropped if constructor theory turns out to be effective is that the only fundamental entities in physics are laws of motion and initial conditions. Of course they are, but there's, in order for physics to accommodate more of physical reality, there needs to be a switch to this new mode of explanation, which accepts as a scientific explanation more than predictions. So the idea of prediction will be complemented with the idea of statements about what tasks are possible and impossible and why. One question might be what sort of how do you test constructor theory? Well, so constructor theory has a status that is that of underlying theories like quantum theory, general relativity, and possibly others, maybe better ones. So it's more fundamental than those, and it underlies them. And the way it does so is by being a theory of principles. So it expresses statements that are of the form, they are a bit like the principle of conservation of energy, statements that constrain theories. And so in fact, some theories are just incompatible with constructor theory, with its principles. As I said, so constructor theory informs the experiments in not a direct way, because it doesn't make predictions directly, but it provides principles. So just like you would go about testing certain principles, such as the conservation of energy, or you can in fact indirectly test constructor theory by testing the theories that obey it. So one way it could be tested is take one particular principle of constructor theory, for instance that of the interoperability of information, that has to do with the very fact that information can be copied. Now that principle might imply that there must exist certain particles which we don't know yet about, but they are necessitated for this principle to be obeyed by our best current fundamental theories. So this would be a way in which constructor theory could be tested, because then you could test whether or not such particles could exist. And so, in other words, more generally, the way you test constructor theory is the way in which you test principles. Yes, it's a meta level, but the proposal is that science is also that meta level, and that principles of physics, such as the principles of thermodynamics, the principle of, some of the constructor theoretic principles maybe, are part of our of fundamental physics, and because there's a way of testing them, and because they inform discoveries of future theories too, because future theories must obey those principles, and so that's why they are part of science. Yes, constructor theory is quite radical, and so one might wonder what sort of what are the ideas in the established way of doing physics that are threatened by constructor theory? Or so I think there's not such thing as threatening, like existing ideas. So I see more like a complement. But if you want to consider what are the ideas that constructor theory would possibly replace if turns out to be effective, as I said. So there's a tendency towards doing physics, well, to considering physics as applying to a narrow set of things, particles and elementary interactions and so forth, and in regarding a scientific explanation as valid only if it is expressed via predictions. And this is part of the reasons why part of the scientific community has still problems with quantum theory, and also part of the reasons why Darwin's theory of evolution, for example, is not considered by some as a satisfactory scientific explanation, because it doesn't predict the existence of elephants at time t in the universe. Yet it does explain how they come about from simple initial things. So I think if constructor theory turns out to be to work, this narrow view of physics will have to be dropped. And this is something that reductionists are not very happy about. And so I think that's actually quite a challenge for us for David and me, to show that there are problems, scientific problems, that can be addressed by constructor theory without resorting to predictions. For example, this whole issue of what it means for information to be physics. We've just come up with this proposal that what it means is that there are interactions and regularities in nature which allow the existence of information to be, in the world. And a way to go about and expressing those is by using constructor theory, and it turns out to be the only effective way, because these properties of nature that we are conjecturing are counterfactual properties, and they must be expressed in terms of possible and impossible tasks rather than in terms of predictions. Another example is the mode of explanation of Darwin's theory, I said, because in Darwin's theory of evolution, you do explain the existence of the appearance of design in the world without the existence of a designer, without the existence of an intentional design process. But you do not do so by predicting the existence of such entities, because if you could predict them with some probability, that might mean that in fact you have design in the laws of physics. So what you actually do is you explain how it is possible that they can arise in our world. And that's a different perspective. It's a constructor theoretic way of explaining things. And even von Neumann, when he was thinking about self-reproduction, he pioneered the idea that self-reproduction must occur in two steps, by first copying what we call now the DNA sequence that codes for the organism, and then by executing the recipe that's inside the DNA to construct a new instance of the organism. He didn't use predictions, the mode of explanation by predictions, in order to explain this. He used a computational model to simulate this process. And because he had an understanding that this was a fundamentally different question from one that you would answer by only making predictions. So the bottom line is there's a whole set of issues that are perfectly, there are scientific questions that cannot be answered by predicting things. And I think that one of the proposals that are implicit in what David and I are doing is that it's fundamental for physics to tackle those questions, and therefore it's a fundamental thing to go about and search for different ways of addressing problems in fundamental physics, and constructor theory is a proposal for that. We are planning to apply constructor theory to other problems in fundamental physics, and one is this idea of how do you make sense of probabilities in fundamental physics. So probabilities have been a hard concept to pin down, and also they are fundamental to certain way of looking at quantum physics. But actually quantum physics is a deterministic theory, so one question is how does one connect the testing of quantum theory, which one way or another relies on the idea of probabilities, with the fundamentally deterministic structure of quantum theory. And this question has been tackled in different ways, but there's still a controversy about that. And we are hoping to apply constructor theory to this issue in order to sort it out. And then there's also this interesting object that's called the universal constructor, which is something that can perform all tasks that are permitted by laws of physics. It's a bit like the generalization of the universal computer, but it doesn't perform only computational tasks, but also tasks on physical systems. And the question is it possible, given the laws of physics that we know, and what's its minimal instantiation? Is it very small or what? So those are questions that we are thinking about as potentially, as the ones to which constructor theory might make a difference. Actually, constructor theory was originated initially was conceived as a generalization of quantum computing. Actually, turned out to be much more than that. But there is, as I said, some very promising trait of this theory of information that we have constructed, which could be applied to understanding issues such as what is the thing that makes a quantum computer powerful as it is. There is a controversy about this issue. Is it entanglement? What sort of entanglement? And there's also a difficulty at the moment in expressing what entanglement means in terms of information theoretic concepts. But precisely because we've related exactly quantum information and classical information, there'll be a possibility to address these questions on a more solid ground. We are searching for a quantum computer in a too undirected way. We don't have a sophisticated theory about what to search for and what are the features of quantum physics that we need in order to power the quantum computer. Of course, we know how a quantum computer works, but that's different from knowing what are the features of a quantum system that you must get right in a lab in order for it to work as a quantum computer. And my guess is that the reason why we haven't yet managed to find a viable realization of a universal quantum computer is that we are lacking this broader and more encompassing view of how quantum information actually works. And so in a way, constructor theory is working towards improving on that. It's a radical idea, and we are working very hard to making it understood by the scientific community. And the plan is that, well, the fundamental thing is we'd like to apply it to problems that haven't been solved so far and show by this that actually it works. Because at the moment people are just wondering whether, they're saying it might work, let's see. We're hoping to persuade the scientific community that this is a worthwhile approach by showing that it can solve problems that couldn't be solved before. And So that's what we're up to now. The theory is still in its first stage, and so we are. The short-term plan is, as I said, to apply it to as many problems as possible and show that it can make a difference. There are actually interesting questions related to, for instance, the origin of life, to the question of fine-tuning of the laws of physics that could be benefiting from a constructor theoretic approach. And we've had some interesting comments from other groups in the world working on these things, such as Paul Davis's group, saying that constructor theory seems very promising in this regard. And so, if it turns out to be working, then more and more people will be using it, and that's what we're hoping for. I've had a unconventional path in physics. I'm a theoretical physicist. I'm a quantum physicist. I've been studying in Turin. I got my master's there in actually physical engineering, and then I moved to Oxford for this PhD in quantum computing with Arthur Eckert. And there is where I met David during my PhD, and we started collaborating on constructor theory. And since the collaboration was very fruitful, we decided to extend it after the DPhil, and so here I am. I'm now working on constructor theory together with David. We're hoping that this will be, fruitful, and it will be capable of delivering this new theory of fundamental physics.